Hello viewers, welcome back to the course on scientific computing and using MATLAB. So in the previous class we have discussed about the Gauss-Seidel method and the Gauss-Jacobi and their convergence, the necessary condition for convergence. So today we will make the MATLAB code for that one, but before that today I will make the MATLAB code for Gauss-Jacobi method, and in that method we will going to solve this system. So I am going to take this matrix as -2 1 5 4 -8 1 and then 4 -1 1. So that is my A, and B I am going to take 15 -21 and 7. So this is a 2 -1 5 2 -2 1 5 4 -8 1 4 -1 -1, and this is the right hand side. So if I take this one, basically my system is this. So -2x1 plus x2 plus 5x3 is equal to 15, 4x1 minus 8x2 plus x3 is equal to -21, and 4x1 minus x2 plus x3 is equal to 7. So in this case I want to see that whether this matrix is a diagonal dominant or not. So if you from here I can see that this part is even less than sum of this, so it is not diagonal dominant. Or even if I change this matrix into this form, I will take it interchanging the rows. So maybe I will change this row here, but because in this case also this is okay, it is diagonal dominant, but it is not diagonal dominant. So suppose I take 4 here, -1 1 and then 4 -8 1 and then -2 1 5. So I have interchanged the first and this and this row I have interchanged. So from here I can change this one, and now if I try to find out, so I can see that this is sum of greater than this, 8 is also greater than this number, and 5 is also greater than this number. So this matrix is diagonal dominant. So if I take this matrix instead of this matrix, then my Gauss-Jacobi method will converge, definitely converge. So Gauss-Jacobi method will converge. So this one I can see from here, and if this will converge, then definitely I told that the eigenvalues will be less than 1. The spectral radius will be less than 1 for the Gauss-Jacobi method, and where my H is equal to minus D inverse L plus U. So that is my corresponding matrix. So now I am going to deal with MATLAB code for Gauss-Jacobi. So let us go to the MATLAB. So I have made this code already for you. So this is the function I am defining, Jacobi. I am giving the name Jacobi. So I have to input what is that A value, the matrix, the right hand side vector B, and this is x naught is the initial approximation I am going to start with, and this is the tolerance value I am going to give. Because this is a iterative process, so I need to give this initial condition and the tolerance, and the output will be the solution. So, I have written there that input is a matrix that should be non-singular matrix, and my Ax should be, this is my system, B is my right hand side vector, and x naught is the initial guess, the column vector, and this is the tolerance. So, I am passing all the column vector here. Now, what I do? I take the length of B, so that is my n. So, this is n I have defined, because it should be a square matrix. Now, what I do? I take a new vector x new with all values 0, and it should be a column vector. So, this is n and 1. Now, I start with the iteration. So, iteration is 0, and for the, just to start with this process, I just take the error equal to 1, because later on I will tell you that why I am writing this one. Now, I will display that the initial guess is x naught. So, x naught will be the initial guess, and I am putting this value in the x old vector. Now, I do the iterative process. So, this is my while loop. So, in the while loop I say that if error is greater than tolerance and the iteration is less than 100. So, I am keeping the maximum iteration here, that is 100. So, if both the conditions are satisfied, only then it will go to this loop. So, that is why I am putting the error equal to 1 here, so that this both the condition will be satisfied, and then my loop will start. So, I just to start with the loop, I will give the value error is equal to 1. Now, I will go to the while loop. Now, this is my for loop. So, I will go from 1 to n, and x new means the left hand side of the iterative process should be equal to bj. I told you that bj is the right hand side element minus a with the same row. So, that is the jth row, and all the columns except the jth column. So, I am putting a 1 to j minus y and j plus 1 to n. So, only leaving the jj column from here. So, this multiply by the x old. So, x old will be same as the same argument, this one, this indexing. So, the same indexing x old should be 1 to j minus 1 and j plus 1 to n, because we have to divide this number by this. So, I am taking all these numbers here, and then I am dividing by the diagonal element, and that is a j j. So, in this case what I am doing, I am giving the old value of the x and I am getting the new value of x. So, after this for loop, I will go to the error. So, error I am finding x new minus x old, the norm. So, the norm means that it should be, it is the L2 norm, and I am taking the L2 norm. So, absolute value and giving the error. So, that is my error value. So, error value is there. Now, so they no need to write the absolute here, because norm will be positive. Now, I am putting x new transferring to the x old, iteration is increased by 1, and I am writing the error at the iteration, at this iteration step is this one. Now, I will go to the while loop again, doing the same process again and again until this condition is satisfied. So, now suppose my error is reduced and this error become less than tolerance. So, I will stop here, because in this case this condition is not satisfied and condition, and it will stop, or my iterations are too large and it is going more than 100. So, in that case also it will stop, and the answer I will get. So, x new, whatever the value of x new is there, that will be go to the x, and this will be the output of my code. So, that is the Gauss-Jacobi method. So, it is very small code for this one. Now, I will go to the main code from where I will call this function. So, if you remember, last time I made this linear system code. So, that will solve all the linear system. So, now we have to do the iterative process. So, that is I have commented the previous one that we have used for the direct method. So, this is my clear all, and that is CLC. Now I will going to start with the iterative process. So now this is the matrix I have started with -2 1 5 4 -8 1 and 4 -1 1, and the right hand side vector is the column vector. So this is what I just started on the slides. So now so this is my initial value I am passing. So for example I am taking 1 1 1. The tolerance I am defining is 0.0005. So it means that is half into 10 raised to power -3. So that is my tolerance, and from here I am calling Jacobi method A, B, x naught and tolerance. So I am passing my A, B, x naught and tolerance, and then from there I am displaying that whatever the solution I will receive, that is the solution. Now I have to find out the convergence matrix. So for the convergence matrix, so this is the convergence matrix H I am writing. N is the length of the B, L is the matrix n cross n matrix, D is n cross n matrix, U is n cross n matrix, and I am defining with the 0, because I know that in the diagonal elements, except the diagonal, all elements zeros. In L also most of the elements are 0, U also. So now I am writing this for loop. So for I is equal to 1 to n, for j is equal to 1 to n, when I is less than j. So when I is less than j, it means I am talking about the upper triangle matrix. So my Uij should be same as Aij. When I is equal to j, it means I am talking about the diagonal elements, then it should be Dij should be equal to Aij, this one. Else the lower triangle matrix, so Lij should be equal to Aij, and then I will end this if loop for 4, and from there I will get the matrix L, U and D, and then for the Jacobi method I know that my convergence matrix is minus D inverse into L plus U. So that is my method, that is my convergence matrix, and then you based on this one I want to find the eigenvalues of this matrix. So this is the command in the MATLAB EIGH. So it will give the eigenvalues of the matrix, and I am showing the display here that eigenvalues of the convergence matrix H are this value. So this is I am doing. So let us run this code. So I run this code one, and then so this is the solution I am getting. So I am starting with the 1 1, and the error at the first iteration is very high, it is 6.65. Then as it is increasing, the error is going to increase, and after some time you see that error becomes very large number. It means that this process is not going to converge, and maybe after 100 iterations this is my error. So it is infinity. So this process is not going to converge in this case, and my x, the solution will be this one. So this is, you know, that why it is happening, because the whatever the matrix I have defined. So this is my matrix A. So I told you that this matrix is not diagonally dominant. So if the matrix is not diagonally dominant, that it may or may not converge. So it depends upon that, it may converge or may not. So in this case I can say that my Gauss-Jacobi method is not converging, and this is the eigenvalues I am getting. So magnitude is quite high here. If you see, this value is imaginary part is 3, and in this the value is 0.1. So real eigenvalue is okay, it's 0.1, but the method is not converging, so I cannot talk about this one. So now if it is not converging, so let us do the interchanging of the rows. So let us do this one. Now I change the rows. Now let us write this one. So now you can see that 4 -1 -1, so that is okay, diagonal dominant. This is also diagonal dominant, and this is also diagonal dominant. So if I interchange the rows, the right hand side vector will also change, and now I take the same process and I run the code. Now you can see that my system, the error is after the 9th iteration, my error is this one, and I get my solution. So it is 1.99, 3.99, 2.99. It means the solution is 2, 4 and 3. So my system is converging, and if you see the eigenvalues, so these are the eigenvalues. So real eigenvalue is 0.3347. So the maximum eigenvalue in this case, the real is this one, and if I take the magnitude of the complex eigenvalue, so that is also less than 1. So because in maximum eigenvalue we can talk about only in the real number. So this is the eigenvalue we consider, and its value is 0.3347. Now the same process, suppose I increase my tolerance and I want my accuracy up to 4 digit. So let us run this code. Now you can see that the number of iteration becomes 11, and that is my solution. Now I am getting the exact solution 2, 4, 3 after the 11 iteration, and the eigenvalue will be same because eigenvalue is not going to change. Now maybe I can increase my another tolerance, and let us see what will happen. So in this case I get my 15 iteration, and the solution I am getting is this one. So in this case my matrix is diagonal dominant, and my Gauss-Jacobi method is going to converge. So that is what we have done with the help of this MATLAB code. Now maybe I can change some another matrix, and let us see that what will happen. So I will stop here with this one, and then I will take the another matrix, and this is a 1, 2.3, 2, 3.45, and this is the right hand side vector. So let us see what will happen in this case. I will run this one. So see, now in this case also I am getting my error is very large, infinity. So this system is not going to converge. And if you from here you can see that the eigenvalue is largest eigenvalue in magnitude is 2.25. So if I see here, then this should be less than 1. If the system will converge, then its value should be less than 1. So in this case my matrix is not a diagonal dominant. Now I will change this one. So let us if you see from here, it is 1, 2.3, 2, 3.45, okay, and 0.35, 2.1. So let us see what will happen if I just interchange the row. So I will take 2, 3.4, 5, and then I write 0.3, 5, 2.1, and then I take 1, 2 and 0.3. So this I have changed now. So in the previous, if you see, my A was this one, 1, 2, 3, and my B was this 2.3, 3.4. So now I have changed this one. Now 2, 3.4 this, so 3.4 should be now here. So it is 3.4. Then another is 0.3 this, so 1 should be there and 2.3 will be there. 2.3. So let us see what will happen here, because the matrix is not diagonal dominant. So in this case also you see that then the matrix is not diagonal dominant, and the Jacobi method is also not converging. And if it is not converging, then necessarily it is necessary condition that you are not getting the eigenvalue, maximum eigenvalue less than 1. So, in this case I can say that this matrix is not diagonally dominant and my Jacobi method is not converging. So, now maybe I can take another system. So, let us take another system. So, I am taking 5, 1.2 and 3.4. So, this is the first equation I am taking. So, let us take the bigger one. I am taking the 7, 1.2, 3.4 and maybe I am taking minus 3.1. So, I am taking it. So, this is the first row I am taking. The second row I will take as 2, 8.5, 3, 1.9. So, this is the second row. The third row I take 3, 1.9 and then I take 6.7 and then I take 4. So, this is another row and the last row I take 1, 0.95 and then maybe I will take 4. So, this is the matrix I am taking and then I take B vector. So, B vector I am taking as, suppose I take 1.33 and then 2.43, then 0, then 1.5. So, this is the vector I am taking with the column vector. So, let us see what will happen in this case. So, this is the initial guess is because it is 4 4. So, I just take the initial guess like this. You can take any initial guess, does not matter. So, that is the solution we are getting. So, after the 36 steps you see that my error reduced to this value and that is my solution. Now, in this case all the eigenvalues are complex except no. So, we are getting the 2 eigenvalue real. So, it is one eigenvalue this and the another eigenvalue this. And you can see from there that the largest eigenvalue in the magnitude is this one and that is value is coming less than 1. So, because the system is convergent then it is necessarily that the largest eigenvalue will be less than 1. So, from here I can say that necessary condition is well satisfied for Gauss-Jacobi method and my Gauss-Jacobi method is convergent for this matrix. So, if you see that this matrix I have made is a diagonally dominant and that is why the Gauss-Jacobi method has to be converged because this is the sufficient condition for this one. So, this is all about the code for the Gauss-Jacobi methods and maybe in the next lecture we will talk about the other code, the Gauss-Seidel method and other related concept. So, thanks for watching this, thanks very much.